Document provides a comprehensive analysis of the Starship explosion, specifically focusing on the failure of a pressurized nitrogen tank, COPV, Composite Overwrapped Pressure Vessel. The explosion occurred on Wednesday, June 18, 2025, at approximately 11 p.m. Central Time, involving Ship 36, a prototype for SpaceX's Starship Mars rocket. The incident took place during preparations for a static fire test at the company's Starbase facility in Texas. This analysis aims to determine the root cause through a systematic examination of existing evidence, contextualizing it with the Starship program's history, and identifying critical areas for investigation. 1. Key evidence and initial clues from the Ship 36 explosion. The immediate and primary evidence points to a COPV failure in the vehicle's payload bay, which contained gaseous nitrogen. Initial clues suggest potential causes related to design flaws, inherent weaknesses in the COPV's engineering unique to this specific design, manufacturing defects, issues arising during the production process leading to a compromised tank, or handling or installation problems, errors during the assembly or integration of the tank into Ship 36. A critical piece of information is that the COPV failed below its proof pressure, strongly indicating a pre-existing weakness, material degradation, or an unexpected contributing factor that reduced its structural integrity below expected thresholds. Flight data will be crucial to ascertain the exact pressure at the moment of failure for comparison with design specifications. The explosion bore a similarity to a 2016 Falcon 9 COPV rupture, raising questions about recurring failure mechanisms for SpaceX's pressure vessels, even if the specific design is new. The location of the failure in the nose cone area, payload bay, and the observation of two distinct explosions in rapid succession, first near the vehicle's nose, then a second eruption of flames and debris on the left side, suggest a complex event. This could imply an initial COPV rupture triggering subsequent failures or interactions with other systems, or a primary failure leading to the COPV's secondary explosion. The blast destroyed Ship 36 and caused significant damage to the test facility infrastructure. Finally, the explosion occurred during a propellant loading process for a static fire test. This highlights the importance of reviewing the specific operational procedures, environmental conditions, and any deviations from standard protocols during this critical phase. Ship 36 was intended for Starship's 10th flight test, previously scheduled for late June, and this explosion has now profoundly impacted those plans. 2. Context of Starship program failures and anomalies. This latest failure is not an isolated incident, but rather occurs amid a series of other significant setbacks that have plagued the Starship program since 2020. SpaceX has lost 9 Starship prototypes to explosions during various phases of development and testing, including SN1, SN3, SN4, SN8, SN9, SN10, and SN11 between 2020 and 2021, in addition to the recent integrated flight failures and Ship 36. Previous integrated flight failures include Flight 7, in January, suffered harmonic vibrations in the propellant system, leading to an explosion after launch. Flight 8, in March, faced a cascade of engine failures, causing a mid-flight explosion. Flight 9, in May, had a propellant leak that caused the rocket to tumble and break apart over the Caribbean. The only fully successful mission mentioned was the 5th integrated test flight in April 2024, where Ship 30 successfully splashed down in the Indian Ocean and its booster was successfully caught by the launch tower. An anonymous industry official observed that SpaceX's development appeared to be moving backward, noting that ground explosions of this nature had not occurred for years before integrated flight tests began. This represents a significant anomaly, a return to ground test failures after a period of focusing on flight tests, suggesting potential new issues in ground operations, component quality, or test methodologies. Elon Musk's characterization of such catastrophic events as just a scratch, and the company's term rapid unscheduled disassemblies, RUDs, present a cultural and managerial anomaly. This approach contrasts sharply with the rigorous halt and investigate philosophy exemplified by NASA's Apollo program after the Apollo 1 fire, raising questions about the depth of root cause analysis and corrective actions being implemented. 3. Cross-examination of evidence, clues, and anomalies. A thorough investigation requires a cross-examination that links the immediate COPV failure to the broader context of the Starship program's history. COPV design integrity versus systemic stressors. The COPV failing below proof pressure for a first time ever for this design suggests either an intrinsic flaw in the new design or unexpected external stressors during propellant loading that significantly reduced its capacity. Given prior flight failures involved propellant system vibrations, Flight 7, engine failures, Flight 8, and propellant leaks, Flight 9, it's crucial to investigate if the COPV's failure was an isolated design flaw or a consequence of or exacerbated by broader systemic issues related to propellant handling, pressure fluctuations, or unforeseen dynamic loads during the static fire preparation. The reemergence of ground test failures, the return to a ground explosion after a period of integrated flight tests, is a critical anomaly. This necessitates a deep dive into any recent changes in ground test procedures, propellant loading sequences, component procurement, quality control, or personnel training that might have introduced new risks or overlooked existing vulnerabilities. It also raises questions about whether the aggressive testing schedule is leading to a less rigorous approach to ground operations. The two distinct explosions phenomenon, the observation of sequential explosions nose, then left side, implies a chain reaction. Determining the precise sequence of events, whether the COPV failed first, triggering other components, or if another event initiated the COPV's failure, is paramount. High-speed camera footage will be vital for this timeline reconstruction. Management philosophy and safety implications. The company's public framing of failures as rapid unscheduled disassemblies and Elon Musk's "just a scratch" comment, while not technical clues, represent a cultural approach that prioritizes rapid iteration over potentially slower, more exhaustive investigation. This raises a critical question. Is this philosophy inadvertently contributing to a recurrence of fundamental issues by potentially not fully internalizing lessons from each failure before proceeding to the next test? The contrast with the Apollo program's response to failure, halting tests, fundamental redesigns, highlights this potential systemic issue. 4. Evidence to examine and potentially uncover new data. To gain further insights and perform the necessary cross-examination, the following types of evidence are crucial for detailed examination. Test stand data. Comprehensive telemetry from the test stand and Ship 36 itself, including pressure, temperature, strain, vibration, and flow rates leading up to the explosion. High-speed footage. Detailed visual evidence capturing the explosion's progression, point of origin, and the exact timing and nature of the initial failure mechanism and subsequent events. Physical wreckage. Meticulous examination of the debris to determine the failure mode, example ductile fracture, brittle fracture, fatigue, material properties, and any evidence of external factors or impact points. Witness accounts. Thorough interviews with all personnel and witnesses involved in the propellant loading and static fire test preparations to gather human insights and identify procedural deviations. Manufacturing and quality control records. Detailed documentation related to the COPV's production, including material certifications, inspection reports, and historical performance data for similar vessels to identify potential defects or inconsistencies. Procedural documentation. Review of all operational procedures for propellant loading and static fire tests, including any recent changes or deviations. 5. Financial and political context. The Starship program operates within a significant financial and political landscape. SpaceX has received over $22 billion in federal contracts, loans, subsidies, and tax credits since 2003, $15 billion from NASA, $7.6 billion from the Department of Defense, with annual government funding ranging from $2 billion to $4 billion in recent years. The Starship program specifically received approximately $4.1 billion in direct federal funding through a Space Force rocket cargo development program and a NASA contract for the Artemis program's moonlander. Despite NASA having its own moon rocket, Starship's failures have left the Artemis program without a suitable lander. The article critiques SpaceX's aggressive testing schedule and public relations, suggesting it prioritizes investor confidence and government contracts over rigorous scientific work, drawing a stark contrast with historically government-led, scientifically methodical programs like Apollo. This financial and political context could be a factor influencing the pace and methodology of the Starship development, potentially impacting the thoroughness of failure investigations and the implementation of robust corrective actions.